Justin Miller here, Oxford College Physics. Going to be looking at some refraction in this segment. So continuing on with some optics. So let's take a look at something here. I'm going to go ahead and take this. So this is some transparent material. You can see through it. It's got a white back because it's got a nice magnet on it. But ultimately, it's transparent. And what we can do is we can take ourselves some laser light. See if I can do this without having to make it dark. So we've got that the light ultimately shines right through this. Goes right through it. You can kind of see the beam as it goes through right there. Hopefully you can kind of see it. There we go. That makes it a little bit more obvious. What comes through, there we go. And what we want to look at specifically is what's going on inside there. So right now it just looks like it's going straight through, following the same path that it enters at. Let me go ahead and change the angle that it's striking this interface boundary right here at. And not worried about this reflection part, more concerned about it going in, following this path, and then what does it do? It changes its direction. Look at, this is the direction that it's initially traveling, and then when it enters this, it seemingly changes its direction. Then it exits over here and changes its direction again. This change in direction is known as refraction, and it is specifically due to how the light interacts with this material. Now, as light travels through free space, it doesn't have anything to interact with. It travels at its normal speed, we'll say. Speed of light in a vacuum, speed of light in free space is known to be approximately, to three significant figures, 300 billion meters per second, and we'd say 3 times 10 to the 8th meters per second. So speed of light in free space is C, 3.00 times 10 to the 8th meters per second. When light travels through other materials, however, it has a tendency of slowing down. Say that it travels at a slower rate. Than in free space. The change in speed at the interface boundary ultimately produces, or may produce, a change in direction. Change in speed at an interface boundary may produce a change in the path of light. This change in direction is known as refraction. And it is explicitly to do with light changing its speed as it goes from one material into another. Now we say it may change its direction. Ultimately, as we saw, it really depended on the direction that light was initially traveling. If it travels and strikes this interface boundary here at the angle of 0 degrees with respect to the normal, say at normal incidence, it just goes straight through, unchanged in its path. But if it strikes it at a non-zero angle, then we get that it does undergo a change in path. We can get all sorts of funky stuff going on with reflections and stuff. We'll look at that. But that's what we've ultimately got. So, we've got a law of reflection. Excuse me, refraction. Which is known as Snell's law, named after Mr. Snell himself, which says that n1 times the sine of theta 1 is equal to n2 times the sine of a theta 2. Well, we got to know what these n's are and how to interpret this expression here. n1 and n2 are known as indices of refraction regarding material 1, number 1, and material number 2. Materials 1 and 2. So first off, let's focus ourselves on this index of refraction. The index of refraction of a material is defined as the ratio of the speed of light in a vacuum to the speed of light in that given material. So it's defined as n is the index of refraction, c is the speed of light in free space, and v is the speed of light in the given material. So n, index of refraction, c, speed of light, in free space, and v is the speed of light in the given material. For which we're defining the index of refraction. So here's a little for instance. The index of refraction of free space is equal to unity, 1. Because the speed of light in free space would be c, we'd have index of refraction of free space would be c divided by c, which would just be 1. Now if the light's slowing down as it travels into other materials, we find that the index of refraction will always be greater than 1, unless we're talking about free space. So we have that n, I'll just say that v is less than or equal to c, so n is greater than or equal to 1. So the reason that we define this index of refraction is because it ends up being very nice quantities, ranging from 1 to 2 to 3 when we're talking about visible light. So very small, nice numbers that are easy to deal with. Where the speed of light is a very large number, number 1, and is still a very large number as light travels through different materials. So if this number here is not some little number, it's still of the order of 10 to the 8th meters per second. And well, let's take the ratio of the two to find a number that's a little bit easier to utilize and call it the index of refraction. There we go. So this is what we've got. We've got the index of refraction is explicitly connected with the speed of light in a given material. And then we've got n1 times the sine of theta 1 is equal to n2 times the sine of theta 2. Let's take a look at this and see how this is composed here. And then go from there. So I can take some interface boundary between two materials. I can take this to be material number 1. Take this to be material number 2. This is the boundary that separates the two materials. Keep it like this. And material number 1 has some index of refraction N sub 1, material number 2 has some index of refraction, N sub 2, that correlate with the speed of light in those given materials. And then we can take ourselves some incident light ray, and look at it, and we can go ahead throw in a normal here. Line normal to the surface boundary. And then throw in that same normal down here. Should have done that to begin with. Normal there, normal there. And then what we're going to have is that there is some sort of change in direction that takes place. We have an incident ray, and then we have this being the refracted ray. And what we have here is some angles. We've got this being our theta 1, and this being our theta 2, measured with respect to the normal at the surface interface boundary. There we go. So with this is how we look at this. N1 times the sine of theta 1 is equal to N2 times the sine of theta 2. So if we know the indices of refraction of the material and we know the angle of incidence, we can figure out what angle it travels through the next material relative to the normal of the interface boundary. That's what we want to be able to do. So what we want to do is look at some cases with refraction and see what can happen and some things that are unique as well. So there's a couple different possibilities. So take this and this to be two different materials, having index of refraction N1 and N2, like we just had. And just kind of draw out the same thing that we had. I'll just make it a little bit steeper. So we can have something like this. The ray goes. This ourselves a theta 1 and a theta 2. In this case, we have that theta 2 is less than theta 1. And for this particular case, this will mean that N2 is greater than N1. So this is what we typically have here. I shouldn't say typically, but this is what we'll have for a particular case when we're going from a material where light is traveling at a higher speed into a material where light then travels at a slower speed. So we go from a lower index of refraction to a higher index of refraction, and we will have that the ray bends towards the normal, giving us that theta 2 is less than theta 1. It bends inward. Well, we can also have that light travels from a material with a higher index of refraction into a material with a lower index of refraction. We'll look at that too. Normal there. Go ahead and have this angle to be theta 1 and this angle to be theta 2. In this case, it's pretty easy to see that theta 2 is greater than theta 1, which will mean N1 and then N2, which will mean that N1. Let's do N2 is less than N1. So these are the two ultimate cases when we've got ourselves some refraction going on. Light bends towards the normal if you go from a lower to higher index of refraction, which equivalently is light slowing down, or light can bend away from the normal if we're going from a higher to a lower index of refraction. In essence, the light is speeding up as it enters this material, it produces this refraction here. So these are the two cases that we'll be looking at a whole bunch. So let's just take a nice little look at that. See if I can get this to work. So, let's see. I want to focus on what's coming out here, this side, because this is looking at light traveling through this material, which is traveling in this path right here, and then it exits, and what does it do? It travels along this path. If we look at it in terms of the direction that it's changing into, it's bending outward, away from the normal of this interface boundary right here. So I can make it a little steeper, there we go. So light's traveling this way in the material, and then that way as it exits. So we're going from a higher index of refraction into a lower index of refraction. That's this case. While entering here, we're going from a lower index of refraction to a higher index of refraction. It's bending inward towards the normal. So that's what we've got going on, these two different cases. Just a matter of what's light traveling from and what's it going into. All right, one more thing that we can look at is some limiting cases in this extent. If we keep on increasing theta 1 for this particular case, where N1 is less than N2, we're going from a lower index of refraction to a higher index of refraction. If we keep on increasing this theta 1, well, theta 2 is going to keep on increasing. That's great. And there's some maximum amount that theta 2 is going to be able to achieve, based upon theta 1 being just about 90 degrees. That's great. Also, as we make theta 1 smaller, we'll get that theta 2 continues to get smaller as well, until theta 1 is equal to 0 degrees, at which time theta 2 will be equal to 0 degrees. Sine of 0 is equal to 0, so we've got to get 0 degrees there. So not too much can happen with this. Let's take a look at this case. Well, as we make theta 1 smaller here, theta 2 will also get smaller, and as theta 1 goes to 0 degrees, theta 2 will also go to 0 degrees. So that's the same thing that would happen here. Sine of 0 is equal to 0. But let's look at what happens is as we increase theta 1. Well, as we increase theta 1, theta 2 is going to increase as well. But there's some maximum amount theta 2 can increase into, and that's 90 degrees. Theta 1 isn't going to be 90 when this is equal to 90. There is some theta 1 which will produce a refracted ray that's at 90 degrees, and we call that the critical angle. So when we're going from a higher index of refraction to a lower index of refraction, we can define the critical angle as the angle of incidence at which the refracted ray is at 90 degrees with respect to the normal. So I'm going from a material with a higher index of refraction into a material with a lower index of refraction. We define critical angle theta sub c as the incoming angle, which will produce a refracted ray at 90 degrees. Say that it produces a 90-degree refracted. So this excuse me. So we can take ourselves some material here. Some N1, some N2, where N1 is a greater than N2, so we're going to be going from a higher index of refraction to a lower index of refraction, and there will be some angle at which this refracted path travels along the top of the surface. So we've got ourselves this theta sub c, and this theta 2 is equal to 90 degrees. That's the limiting case there. Maximum angle of refraction for a particular angle of incidence called the critical angle. So let's look at this. We've got N1 times the sine of theta sub c is going to be N2 times the sine of 90 degrees. Well, the sine of 90 degrees is just equal to 1. So we've got ourselves that the sine of theta sub c is equal to N2 over N1, or theta sub c is equal to the arc sine of N2 over N1, which is only a defined quantity if N2 is less than N1. That's it. So this is how we define the critical angle. Now the question becomes, what happens if we exceed the critical angle? If theta 1 is greater than theta sub c, refraction no longer occurs. Instead, we get what is called total internal reflection. What does that mean? Well, total internal reflection just means that you get reflection instead. It stays in this given material. It doesn't enter this material at all. It just seems like the surface is a mirror in a sense. So if we have, let's draw this again. We've got something like this. Again, N1, N2, N2 is greater than N1. Sorry. N1 is greater than N2. And we exceed this critical angle we get that the angle of incidence is greater than the critical angle, we just get reflection, which follows back to the law of reflection, which gives us this angle relative to the normal is equal to this angle relative to the normal. It doesn't enter this material. That's what we get if we exceed the critical angle. So again, the critical angle is only defined when we're going from a higher index of refraction into a material with a lower index of refraction. Where the light ray will bend away, and the refracted ray being at 90 degrees with respect to the normal means that we're at the critical angle. Exceeding the critical angle, you get reflection. All right, so that's it for right now. Be well.